Welcome to another Great Cow Basic tutorial or demonstration for the 16F171 chip family. Hello, my name is Venn. I'm a co-developer of Great Cow Basic. Today I'm just going to bring out one person in particular, and that's Angel Meir. He's been developing GCStudio and GC Code, the IDE that we're using, and I really think that his 9 months amount of work has been tremendous to bring us forward to the modern age. So I thought I'd mention Angel. So let's get into the PowerPoint. What are we going to be covering? We're going to be covering pulse width modulation. I'm using LEDs to represent other output devices. It's worthwhile peeling back the capabilities of this particular chip with respect to pulse width modulation. We touched on this before at tutorial 10, but we're going to have a deeper look into that with more options. The hardware I'm using is a microchip low pin count demo board, and Chris Roper in South Africa has laid out a breadboard so that you can make this on your own, and you can simulate the low pin count demo board, and then therefore you can follow along. I thought it was worthwhile recapping on this one slide. I showed this slide earlier on, talking about the 171 chip family. It's a high performance PIC. It's got many different outputs, but it's got one particular output that we're going to look at today in this tutorial, which is pulse width modulation. We've looked at it with respect to CCP, PWM, but it's got 16-bit as well. But there are other options that you've got with Great Cow Basic. We want to look at how we configure and how we use. So it's worthwhile looking at that overview of the chip again. We touched on this at tutorial 10, the way that a pulse width modulated signal is a frequency. It could be a variable frequency, but it's a change in duty cycle, which changes the power ratio. And it really is a succession of pulses, and we're going to see those pulses on an oscilloscope. And it's a method of reducing the average power of the electrical signal by effectively chopping it up into these segmented steps, or via the duty cycle. So the average current that is fed to the device or the load is turned off and on at a high speed rate, and the longer the signal is on compared to the off, the higher the total output or power supplied to that load. What we've got inside of this particular chip is a whole host of other options. There are 5 main operating models on the slide here: left, right, centered, variables, and compared. And you can actually have, let me just think, I believe you can have 8 out of a 16-bit pulse, and you can offset them, and you can time slice them, and you can match them up. So it's a far more sophisticated module than just a standard frequency and duty cycle. They are time independent of the main CPU, so therefore you can generate some extremely sophisticated PWM signals. So in terms of the hardware today, what have I got? I need to show you this oscilloscope again. I've got it hooked into a particular port, and I just picked that one because the LED happened to be on it. So we can have a look at that at the moment. I will just show you my desktop. And if I show you the scope, my desktop may be better. There we go. We've actually got a signal that's currently operating. I've also got the camera operating as well. So I'll show you the camera shortly. The camera itself will be alongside the. There we go. So we can see the LEDs operating alongside our oscilloscope, and that's quite an important feature of validating what we're doing. Back to PowerPoint. So there are at least 4 types of pulse width modulation that you can use within Great Cow Basic. These don't always come so readily in other languages, so it's worthwhile going through them. There's one called the software way. It's quite clever. It actually generates a pulse width signal with a number of pulses. It's just a piece of code that's been in the compiler for many, many years. You don't need PPS. We've touched on PPS before. And you can put it on any port within the constraints of any valid output. And we're going to look at that. And it's very useful if you just want to send a number of pulses in a particular shape, obviously the frequency and duty, to a device. There's CCP, PMW, fixed frequency, fixed duties potentially. You can actually change those on the fly, but you need to use PPS. And it's interestingly, we have what's called I said fixed frequency, and I will show you that fixed frequency configuration. It is extremely simple with two constants. Very low impact on your program, and it just uses, as I said, two constants. We looked at number 3, which was CCP PMW, variable frequency, variable duty, when it's using a particular timer, and we saw that in tutorial 10, but we will recap that in these options. And finally, there's a pulse width modulation using the 16-bit. Huge amount of capabilities. We saw on the previous slide. Yes, you need PPS and lots of them, okay? And you need lots of parameters. So many that there is no library within GreatCAD Basic. So what we're going to do is write direct to the registers. So it's a very interesting use of GreatCAD Basic. And with that overview of those 4 different ways, we're going to walk through these 4 examples. Examples 120, we saw that before, 245, 240, and 250. And we'll look at the results as we go through. So let's go out to my desktop and get started. Move that aside. GCStudio comes up, and I'll just zoom in on my desktop so you can see it. I do other work, by the way, and you can see I do because the list is getting longer. I need that one. D. That's where my files are. Now, Angel Mia, my co-developer for the IDE, has told me a couple of things, right? And I'm going to touch on those as we look now. So as you can see, there's a white IDE. Well, I'm going to change it back to the black that we normally have. I'm going to do that, but also I'm going to turn on something that he's taught me this morning, which is around screencast. So I can press function key F2, type in toggle screencast mode, and it would change the way that the IDE is operating. Now I'm going to change the color. Control K, Control T. You can see that on the screen. So now I'm going to pick my dark default, and I'm back to the dark Visual Studio that I had previously selected. So now with the screencast mode on, you can see where I'm clicking as well. So let me just go into the Explorer, click in here, Control F, .gcb, and I'll do it properly, Control F, .gcb, and apply the filter. Now I've only got the source code. Now I said I'm going to walk you through a whole series of demonstrations, so we'll start at 120. So if I zoom in for you, I'm zooming in so that you can see the code. Shut the Explorer. The first one we're going to look at is 120. I'm currently here we go, I'm in the editor, and I can cursor through my programs that I've got ready to show you by rotating my mouse by hovering on the top tab. Click on 120. We've seen this before. 120 is the demonstration. The chip. The PPS hasn't changed, because all this one does, if you remember from number 10, it cycles through setting up the hardware pulse width modulation using the value returned from the read ADC. Let's zoom in some more. It reads the ADC, puts it in a value, we scale it, we wait 10 milliseconds, and then we set the hardware. And it's going to do it on channel 1 at 5 megahertz using the value that we defined. And where did we find channel 1? Channel 1 CCP is defined here quite clearly. I put CCP1 on RC0, 2, 3, 0, 1, 2, and 3. And so, if we look at the camera, here it is. I'm going to program that by today. I pressed F5, and that will program the computer, but the controller. It's now programming it. And now, if I go into the scope, we can see the scope operating. So, as I rotate the potentiometer, the duty cycle changes, and that's what we expect. Full on, and as I rotate down, the duty cycle reduces. So what we're doing there in our program is changing the duty cycle and leaving the frequency alone. You could change the frequency as well if you wish, and we saw this at tutorial 10. If we look at the code, we can see that operating, and it's extremely simple in terms of its use, but it has great power because you can now control motors and other output signals. But this is one of many different methods which I want to show you. So let's look at another method. This is demonstration 245, PMW out. It's a long-standing piece of code from Great Cow Basic, and essentially you set the chip up. I'm going to ignore most of the constants until we get down to here. And what this does, you can send out a PMW signal for a specific number of cycles and then turn it off. It's all done in software, and I'll show you the code. It's essentially PMW out is the command. There's more than one channel. Channel 1. I'm going to read the ADC, and I'm going to pass it 100 cycles. It's an arbitrary number. We'll play with this number in a moment. Wait 2 seconds, and then we'll loop around and do it again. I'll show you how it operates, and then we'll see exactly what it's doing. So in terms of the LEDs, we're expecting a flash of 100 flashes, and there we go, on one LED. I'll explain why I've only got one, because that's where my scope's attached. If we go to the scope, we're going to see what's actually happening in the scope. It's pulsing on and off. Then we change the horizontal value, and we can see there's a number of signals in here. Let's go back to the code, change the code, and we're going to change that to 3 cycles, and then we can see exactly this arbitrary number change on the scope. Change it to 3, press function key F5, and back into the scope. And what we're going to see is 3 cycles. Let me change the horizontal value. 3 cycles. I can change it to 2 cycles by simply changing the code. And so if you have a use for a fixed, I've changed the code to 2. If you have the use requirement to send out a number of pulses, PMW out is an essential piece of the compiler. Compile that up. And into the scope, we can now see we've got 2 signals. And let me reassure, if I change the horizontal, we can barely see these 2 operating, but we'll try and get them on the scale here. The scale is currently ½ a second, and it's going to take a long time to show 2 pulses. Let me just think. Oh, there's one. Yeah, the scope is timing out, I think. There we go. I'm going to move on. because the next one I want to show you is fixed. I should show you how we set it up in reality. He laughs. To set this up is extremely simple. You define PMW out 1 as a constant, and you tell it which port you want it on. You set up PMW delay. That's a constant to be added in terms of a microsecond delay after the pulse. And you must just tell it that the PMW out 1 port is an output. It's good practice. It's not actually needed, but it's just for your own mind. It's good to do that, and that's it. That's all you have to do. And then you can send out as many pulses as you like. But remember, this is all done in software. And so I'll revert that back to 100 and save my file later. Let's look at what's called fixed mode. Fixed mode, again, uses CCP PMW, and therefore I have to set up my PPS, which is this set of code here. Standard set off constants, and then there are two constants to set up: the frequency and the duty. And these commands go back to the very earliest PMW capable PICs. And essentially, you set PMW underscore frequency, FREQ, to the frequency you want and its duty cycle. And then you say PMW on. And now PMW will be on within those. That's it. That's all you need to configure it. Let's program that up. Press F5. We'll go into the scope. I'm just going to do an auto to get the signal. And then I'm just going to reduce the, I'm going to take away channel 2 because that's just noise. I haven't got anything connected to it. And just change the gain on there. There we go. So now we can see that we've got a fixed frequency, and the code could be doing something different now. The program could be doing something different. So back to our code. How would we change it? Well, essentially, if we wanted to change the frequency or the duty, we literally change the value, recompile, go back out to the scope, and we'll see that change from a 50% to 25%. It's a superb way of getting a fixed frequency that very easily with the calculations that just aren't necessary with other types of setups. So we've seen three so far. There is CCP, PMW using PPS. We've seen PMW out 1, which is essentially from software. We've seen a fixed mode like this, which is extremely low impact in terms of its setup. Now let's go back to the 16-bit. 16-bit is slightly different. I'm just going to zoom out slightly so that you can see it. The 16-bit is a module that needs to be configured via PPS. I've set up PMW1 16-bit on the 4 LEDs that we've got. I have used PPS tool to do this. I press F4, PPS tool, and then select the option as there. It will then take me into the PPS tool. I have some coffee whilst I'm waiting. So the first thing we're going to do is just validate that we can set up the PPS. So it's the peripheral output. There's PMW1 has 2 outputs, PMW2 has 2 outputs, therefore we could set up 4. I'm going to set up 1 PMW on RC0, RC1, RC2, and RC3. And we've got the code that we require, and that code is the same code that's actually inside of our program. Let's go back to the program. So we've got the PPS setup, essential part. Constants, all very similar. And now what I'm actually doing is writing direct to the registers inside of this PMW module. Where do I get those from? Well, I get those from the data sheet. Let me just get rid of this. How do I get rid of it? Oh, there we go. I've gone to section 29 of the data sheet. I've then studied it, and I've understood the registers that are required. And here it is. These are the registers that I need to set. I need to set up a clock source, a prescaler, a period event in PR and the PR buffer. I need to set up the duty cycle for one side, whether it's got a reset, and where my output is. So I'm going to have to set up 1, 2, 3, 4, 5, 6 different registers. Now, normally Great Cow Basic in the background does all this for you, but these are new modules, and we don't really see the justification, because you need to do this on your own, because these are critical pieces of timing, because you can have extremely complicated and complex timing diagrams created. But essentially, what I've got inside of here, inside of the 16-bit variable mode, are those registered. I've got to disable the external register. I've selected the high frequency internal oscillator. I've disabled auto loading, and then I've set up my PR value to 03E7, and here's the high value and here's the low value. I'm just going to turn back on screencast mode because it seems to have stopped working. Weird. So I've set it to 3E7, and that's been calculated to give me a frequency. I have a prescaler of 32 with no postscaler. Then I've got a series of matches that I could have set up, but I haven't set any of those. They're all set to 0. And then I'm setting up my first duty value to be the same as my frequency. I've done that on purpose so that we can understand how this program works. And the same for the other channel. And then I have turned off all and cleared off all the interrupt flags. You can see if I click on the word interrupt, there's quite a few interrupts that I've disabled. And then finally, I've enabled this particular channel. And that is to set it up normally. We do all that for you in a library. And then what I've got is a program. All this program is going to do is cycle through a variable called PMW value, and it's going to cycle from 0 to the frequency, which is 3E8. It's then going to turn off the module, turn it back on again at high speed, and then it will change the frequency. And then I'm going to come back down from the top value to the low value. Let's see it in action. And then I'll explain one more feature. It's programming it. And now you can see that it's getting darker. There we go. And brighter. So something is causing it to happen. So if we look at the oscilloscope, I need to look at it on my local computer. We can see the oscilloscope is now working as expected. And it's actually the same scale as previously at 1 megahertz because that's what I chose. I did the calculations based upon that. So what are we seeing here? We are seeing that you could write direct to the registers in Great Cow Basic. These are the registers that are in the datasheet. These are the registers that are shown inside a PPS tool. So let's look at, inside of PIC info. So if I press function key F4, PIC info, it will take me into the PIC info for this particular chip. If I look at the registers, and then do a search on the registers, I've just cut and paste one out, And here is one for the PNW. And these are all the ones for the PNW that I'm currently working on. So I've set majority of these, there are about 12 of them, all need setting. And it's not easy to set the 16-bit, but it's easily doable using this as an example. Essentially, as I said, set the frequency, set the duty, set your clock sources using the diagrams in the datasheet. So if I wanted to change the frequency, I would have to recalculate all this, which I'm not going to do live because that would be too dangerous. But one thing I want to show you is the value PMW value. What I've done, I've created a variable called PMW value, and I've created that as a word. A word has got 2 bytes. And I've said that that word is an alias to the duty cycle for one of PMW1's channels. And I said that the high byte is one register and the low byte is the other register. So I've actually created an alias directly into these 2 registers, and Great Cow Basic will do the magic in the back end. So as I change PNW value, those addresses are then therefore updated appropriately. Hence, there is no magic. There is some magic going on in here, but it's relatively simple magic and quite easy. Also, what you saw in the IDE here, Angel's a Genius, we're actually looking directly into the PDF as I can select it from my files, and it's actually in the folder. I just select it from the files, and it is very useful for actually having your operations and your operation documentation within your project. So, big subject today. Let's go back to PowerPoint. So what we want to look at today is using PMW out, using CCP, PMW, using the fixed frequencies, fixed duties, code, and then the 16-bit PMW channels. I can only scratch the surface. What you need to do with PMW is decide what you need. Do you need a high resolution, high frequency, very complicated to set up 16-bit? Then use it. If you just need a signal that's constantly on in the background, you would just use the fixed frequency. If you need pulses, you'd use PMW out. Many different options, but you just need to sit down and figure out what's the right one for your particular project. And with that, we'll call it a wrap to get to close here. And in the next tutorial, we're going to look at memory, reading and writing memory, program memory, SAF memory, and a quick review of EEPROM. And then we'll be closing out with other parts of Great Cow Basic toolchain. And with that, we'll call it a wrap.